Hello, this is Orlando. Today we're going to continue with our series of tutorials on the use of SolidWorks and its flow simulation add-in. We're going to model a Venturi Flowmeter, and we want to validate the calibration curve provided by the maker. With this tutorial, we want to achieve four main objectives. Firstly, we want to generate a 3D object departing from a 2D sketch using the revolve both feature. Later, we will set up a parametric sweep analysis using the SolidWorks flow simulation add-in. Then we want to recover boundary or surface parameters from solution data. And finally, we will obtain the calibration curve for the Venturi Flowmeter. The main specifications of the Flowmeter are shown in this screen, and as you notice, the Venturi Flowmeter features two pressure sensors. Thus, we are going to be able to estimate the pressure drop between both zones. We must perform a parametric sweep by changing the value in the inlet velocity of water to replicate the calibration curve. According to the number of points or the number of velocity values that you provide to the software, we will be able to obtain a plot like this one. Furthermore, we can visually observe the pressure drop within the Venturi Flowmeter in an animation like this one. Remember that you can always go to the technical reference document if you want to get more information about the SolidWorks flow simulation add-in. You just have to follow the route in your computer. Okay, we will continue on the window for SolidWorks. Now we are here in the main window for SolidWorks, and I'm going to select New Part to start drawing our sketch. Remember that we need to replicate this 3D geometry or object, and we're going to depart from a 2D sketch. As we have a condition of symmetry along the main axis of this geometry or object, I'm going to use the revolve both base feature in SolidWorks, and I'm going to depart just from a 2D object. So I'm going to come back here to the window in SolidWorks, and I'm going to select from plane. I'm going to click on sketch, and I'm going to the sketch ribbon, and I'm going to select center line. I'm just going to draw the center line here. I'm going to select this line, and I'm going to activate infinite length. I'm going to select again this line, and I'm going to select this feature as relation, and I'm going to select again this point. So we have two selected entities, the line, the construction line, and the reference point in the origin. And I'm going to make it coincident to avoid the construction line to move from this position as we go ahead in our model, as we move forward in our model. Okay. I'm going to start sketching the first object, and I'm going to select center line. This is the first end, and then I'm going to draw a solid line. Okay, I'm going to depart from this highlighted point. Okay, there you go. I'm going again to the sketch ribbon, and I'm going to select center line, excuse me. Okay. Then I'm going to use the smart dimension function, and I'm going to specify that the distance between the reference point and this line is 7 millimeters. Then I'm going to specify that the distance between this point that is highlighted and the reference point is also 7 millimeters. And the length for that line is 14 millimeters. I'm also going to specify that the length for the first section is 24 millimeters, and for the other side is also 24 millimeters. The radius of this pipe is 12 millimeters. The other side is also 24 millimeters. I'm going to specify the angle here as 10.5 degrees, and on the other side is 7 degrees. And then, well, I think that is already fully defined. Okay, the sketch is already fully defined. And what I need to do now is to go to Features and select Revolve Boss Base. This message says that this geometry is open, and I'm going to select No. I'm going to select the axis of revolution, that it will be the construction line, and the theme feature is already activated, but I'm going to change the value here for the thickness as 1 millimeter, and I'm going to make sure here that the inner diameter is the 12 has a value that I already defined as 12. Here the outer diameter is 12. I need to change this, and I'm gonna click here, reverse direction. Okay, here we have that the inner diameter is 12 millimeters. Okay, I'm gonna click OK, and we have this first part we need. Okay, then we need to draw the sensors for the pressure, and to do that I'm gonna position on the top plane. I'm gonna sketch here, and we can go to circle in the sketch ribbon. I'm gonna draw here a circle. The diameter of this circle is 4 millimeters, and the distance between the reference point and the center of this circle is 46 millimeters. Okay. We can also make another circle here, draw another circle here, beginning from the reference point, and I'm going to specify that it has a diameter of 4 millimeters, and it's already centered on the reference point. Okay, we already have the sketch for both circles, and to extrude them I'm going to position on the features ribbon and I'm going to select extruded boss base. From this list, the from section, I'm going to select offset, and I'm going to type 16 millimeters. I'm going to change the direction of this geometry, and as you can see, it's already changed, but I'm going to specify here in direction 1 section, blind, from this list, I'm going to select up to next. Okay, there you go. I need to activate the thin feature because I need a thickness here. I need the sensors to be hollow, and I'm going to specify a thickness of 1 millimeter. If I activate the reverse direction button, it will change the diameter of these pipes. I need the original one, so I'm gonna click OK. But as you notice, we don't have a hollow surface here. We need to generate the orifices. To do that, I'm going to position here, and I'm going to select the extruded cut function. Here I'm going to specify up to next, and OK. And we already have the orifices on the surface. Okay. We have finished our geometry, and now we must save our work before going ahead. Okay. We are going now to the flow simulation add-in. If you don't have it activated, we are going to the options menu, and I'm going to select add-ins. You're going to look for the add-in here, SolidWorks Flow Simulation, and to activate it, you must activate this checkbox. And if you want it to start up every time you open SolidWorks, you can activate also this checkbox. I'm going to click OK, and you must have this ribbon here. Before going to the wizard, I'm going to create the leads for this geometry. We need to create 4 leads, one for the inlet, the outlet, and the 2 sensors. Okay, I'm going to select here tools and create leads. I'm going to select this surface, this other surface, and these ones. Okay, that's okay. I'm going to click OK. This operation helps the wizard or the flow simulation add-in to select the proper computational domain for this geometry. I'm going to save this work, and what we have to do now is to go to the wizard. I'm going to change the name for Venturi. Click next. Here you can change the unit system that you like to work with. The number, you can specify the number of decimals that you like to obtain from the simulation results. And here in this second window, you can or the third window, you can select the type of analysis that you would run. In this case, it's an internal flow, and I'm going to select that the gravity has a direction only in the y component. Okay, next. For this case, the working fluid is a liquid and is water. The flow type, I'm going to select here that is turbulent only, and click next. In this window, I'm not going to change anything. And in this last window, you must specify what is your reference and temperature, what is your reference pressure and your reference temperature. In this case, the temperature is specified at 293 Kelvin, and the pressure is specified, the reference pressure is specified at 1 atmosphere. If you want your results to be presented in gauge pressure, then you need to change this to 0 pascals. I'm gonna leave it that way, and I'm gonna click finish. Okay, as you notice, the computational domain has already been defined by the software. And if you want to hide it, you can go to the computational domain node, right click on it, and click hide. I'm gonna show it again. And now I'm going to specify the boundary conditions. To do that, I gotta go to the boundary conditions node, right click on it, and insert boundary condition. Okay. I'm going back to this slide to remember that what we need to simulate, or what we need to obtain from this simulation. We are given here with the calibration curve for this Venturi Flowmeter that is provided by the maker. So we need to replicate this curve. So we need to specify different inlet velocities for the water, or different flow rates, and we will obtain the different value for the pressure drop in every case. So if we give 5 different values for the flow rate, we will obtain 5 different points here in this curve. To do this comparison, we need to do a parametric sweep. So I'm going back to this window, and here I'm gonna select that the boundary condition, the inlet boundary condition, will be applied in this phase, and I need to select this one, but in this case we need to make sure that the computational domain, well, that the phase that we select is on the computational domain, inside the computational domain, and in this case it's not happening here. To select the proper phase, I'm going to clear this. I'm going to position on this phase and right click on it, select other, and I'm going to select lead to. Okay. I'm going to select that the type of boundary condition that I'm specifying is inlet velocity, and I can specify here 10 meters per second. Remember, we have to obtain different pressure drops at different inlet velocity values. What we will have to do normally is to change every time this value from, for example, 0.1 up to 10 meters per second. But that will consume a lot of time, and I'm gonna leave it this way for the moment. And what I'm going to do next is to specify the outlet condition. I'm gonna position here, right click on it, select other, and leave 3. I'm gonna click here, pressure opening, and I'm going to specify that this boundary is open to atmospheric pressure. Okay, that's okay. Then I'm gonna activate the section view because I want to select the inner walls and I want to be able to have a free access to them. So I'm gonna position again on the boundary condition node, right click on it, insert boundary condition, and the type of boundary condition will be wall, real wall. In the selection section, I'm gonna select this part, this, and these ones, and I'm gonna click OK. There you go. So I'm gonna define the mesh here, and this is accordingly to the level of precision that you want, and I want, for example, 6. Show basic mesh. Okay, I'm gonna lower a little bit. I think 5 is okay. And okay, I'm gonna hide the mesh. That's all. Okay, now I'm going to specify or set up the parametric sweep. To do that, I'm going to position here in Venturi node, and I'm going to select new parametric study. Here we have these tabs, input variables, output variables, and input variables I'm going to select add simulation parameters. From the list, I'm going to expand the option boundary conditions, inlet velocity, and I'm going to specify velocity normal to phase. I'm going to click here OK, and I'm going to double click here, and I'm going to specify different velocities or different values for the velocity. I'm going to start with 10, 7.5, 5, 2.5, 2, 1.5, 1, 0.5, 0.25, 0.1. Okay, that's okay. You have 10 different values here for the inlet velocity. So we will obtain different values for the pressure drop that we need as we change in the velocity, in the inlet velocity. So I'm gonna move here to the output parameters, and here I'm going to select add results. Okay, it says that we have nothing to add. I'm gonna click here OK, and that's message is because we haven't specified here what we want to obtain. For example, we need to go here to results, and I'm going to select surface parameters. In this case, I'm going to click here, surface parameters, right click, insert, and I'm going to select this face. Okay. And I need to know what is the pressure on this surface. I'm gonna select the parameter pressure and I'm gonna click OK. Okay. If you notice, the message here is that the results are not currently loaded because we haven't run the simulation yet. But it doesn't matter. I'm gonna click OK. And I'm gonna change this name to pressure A. I'm gonna add another boundary, surface parameter, and I'm gonna select this face, this boundary, and I'm gonna select pressure. Okay, this is pressure B. Another useful surface parameter that I need is the mass flow rate, no, the volume flow rate. And in this case, I'm going to clear this selection and I'm going to select this face because I want to know what is the volume flow rate. I was specifying before the velocity, the inlet velocity, but I need to make that conversion to volume flow rate. Okay. Volume flow rate. Okay. I'm going back to what if analysis. I'm going to position on the output parameters tab and I'm going to select add results. Okay, there you have here available the pressure A, pressure B, and flow rate, the volume flow rate parameters that we just defined. There you go. Okay, to summarize, what we've done is to specify the inlet boundary condition, the outlet boundary condition, the wall surfaces, and we specify that we will obtain some results. For example, the pressure A in this surface, the pressure B in the other sensor, and the volume flow rate here in the inlet. Okay, for the parametric sweep or the parametric study, we specify different values for the velocity, the inlet velocity, and we want to obtain accordingly different values for pressure A, pressure B, and the volume flow rate. Okay, here in this scenario you have a summary of all the runs that will be done for this simulation, and here will appear the results. Okay, I'm gonna click run, and we need to wait for the software to run the simulations. Okay, the calculation has already finished. I'm gonna deactivate the section view, and if we click here in this tab, we can see that the pressure values are already displayed for pressure A, pressure B, and the volume flow rate. So we can copy these tables directly from here, and I'm gonna open an Excel work table. Okay, I'm gonna copy in this document this table, pressure A, pressure B, and the volumetric flow rate. Okay. I'm going to generate a table here with starting with the inlet velocity in meters per second. I'm going to copy the pressure A here, is in pascals, and I'm going to copy the average pressure. Then for pressure B, okay. Maybe for the volumetric flow rate, I would like to have more accurate data. To do that, I'm going here. I'm going to copy this data from the generated file in Excel. I'm going to copy these cells. Okay. Remember that here we have meters, square meters per second. Okay. I'm gonna do a conversion here for the volumetric flow rate. It will be cubic decimeters per second, and this is equal to this cell by 1000. Okay. Here I'm going to calculate the pressure drop, also in pascals, and this will be this one minus this. Okay. Then I'm gonna move this one again, and I'm gonna change here the units for pressure, and as you see, we have units of meters of water. To do this conversion, we're gonna divide the value of the pressure drop in pascals by this value, 9,806.38. Okay. And here in this plot we have values for the flow rate, units for the flow rate in liters per second, that is equal to cubic decimeters per second, and in the y-axis we have meters of water. Now we are able to plot the curve and to compare it with the calibration curve provided by the maker. I'm going to copy this column in this column. I'm going to insert a plot. And remember that in the X and the X-axis we have volumetric flow rate in liters per second, but in the manufacturer's curve we only have up to a value of 1.2. So we need to specify here, well, the volumetric flow rate will only get up to 1.12. Okay. I'm gonna copy and paste the original curve. Okay, I'm going to specify here that we have a maximum value of 1.2 and the main units will be 0.2. Okay, I'm going to overlap these curves. There you go, and you need to obtain something like this. I'm just gonna change the markers color and marker without filler color, and the color here will be red. Okay, I think that's okay. If you like, you can delete this part. Okay, there you have. So we've been able to replicate or validate this calibration curve provided by the maker of this Venturi Flowmeter, and this was done using a setting up a parametric sweep in SolidWorks. We're going back here to SolidWorks, and I'm gonna click here, OK, save and close. Well, if you want to run this simulation for the specific values that you specified here in the model, we need to run the simulation. Okay, the solver is already finished, and we want to create an animation with the flow trajectories for pressure. I'm going to right click here and insert and flow trajectories. I'm going to select the inlet face, and I'm going to type here the number of elements that we want to see. Here will be arrows for pressure, and the size, I'm gonna detail preview. Okay, I'm gonna increase the value of the size. Okay, I think that's okay. I'm gonna click OK, and to have a better view of what is happening inside, I'm going to click display and transparency. I'm going to set the value to 100, and I think that I can modify this operation, and I'm going to select 5 to increase the size. Okay, maybe it could be 1. Okay, that's okay. Okay, and I'm gonna right click on flow trajectories and play. Okay, here you can observe how the pressure drops when it comes from the inlet part to the contraction part, and then the value of pressure increases again. Okay. Okay, remember that we wanted to do here was to validate or replicate the calibration curve that is provided by the maker of this Venturi Flowmeter, and we've been able to do this by setting up a parametric sweep in SolidWorks. I expect that this operation is useful for you, and you can apply it in your class of fluid mechanics. And if you have any other question or commentary, you can send me a message to my email. I expect that you are safe and healthy, and I will see you in our next tutorial. Goodbye.